Welcome to the Explainer. Today, we're taking a standard textbook experiment and turning it into a foolproof masterclass, basically to help you absolutely crush your upcoming physics exam. If you've been staring at Activity 12.1, scratching your head, wondering how to unpack all these moving parts for test day, well, you're in the right spot. Let's get focused, break this whole thing down, and guarantee you those points.
Here's our roadmap for this review session. We're going to hit the exam setup, do a step-by-step breakdown, look at a really cool water pipe analogy, nail down some core definitions and mnemonics, and finally, run through some practice exam questions.
All right, part 1, the exam setup.
And moving right into part 2, our step-by-step breakdown. Let's visualize this experiment. So, our ultimate goal here is to prove this hidden, honestly profound link between two fundamental forces of the universe. And your examiner, they want to see that you grasp this big picture before you even touch the tiny details. To do that, we really need to visualize the physical setup you'll be tested on. Understanding the 3D geometry is usually where students lose easy points, so let's get it right. Imagine a straight, thick copper wire placed right between points X and Y in an electric circuit. But notice the specific orientation. The wire is kept strictly perpendicular to a flat rectangular plane of paper. And resting completely flat right there on the paper, right near the wire, is our little compass. Now you'll see the rest of the circuit too, the battery, the resistor, the ammeter. But that vertical, perpendicular wire and that horizontal compass, they are the absolute stars of the show here. The actual steps for this activity are delightfully simple, but hey, precision matters on a test. Step 1, you securely place that thick copper wire in the circuit. Step 2, you place the small compass flat near the wire and just take note of where the needle is resting. Step 3, you pass the current through the circuit by inserting the key into the plug. And step 4, you watch the magic happen. You observe the sudden change in the position of the compass needle. It's a really straightforward physical procedure, sure, but the scientific implications of it are massive.
Okay, part 3, the water pipe analogy.
If you're struggling to visualize how a straight wire affects a compass just sitting next to it, think about it like this. Imagine water rushing straight down a pipe. As that physical current flows rapidly, it actually creates a swirling whirlpool of water around the outside of the pipe. Well, our electrical circuit does the exact same thing. Just like the water, the electric current rushing straight down that copper wire creates an invisible, swirling circular magnetic field right where the compass is sitting. So the wire is the pipe, the electricity is the water, and the magnetic field is that whirlpool catching our compass needle. Makes perfect sense, right?
Moving on to part 4, core definitions and mnemonics. Let's get your exam vocabulary dialed in.
The absolute foundational concept here is electromagnetism. The source text spells this out super clearly. It's the physical link where an electric current passing through a conductor, like our copper wire, literally produces a magnetic effect. So the big takeaway is that this single experiment proves, once and for all, that electricity and magnetism are permanently linked. They're basically best friends, entirely dependent on each other.
Next up, we need to define magnetic deflection. When your test asks you to observe the change in the position of the compass needle, it's really asking you to witness magnetic deflection. It's just a fancy scientific term for the observed physical movement of a compass needle when it's exposed to an external magnetic effect, which ultimately pulls it away from its normal resting alignment.
To lock this into your brain for test day, I want you to memorize this super simple mnemonic device, WCCM. When current comes, magnets move. Let me say that again so it really sticks. When current comes, magnets move. If you blank out while staring at your exam paper, just scribble WCCM in the margins. It's going to instantly remind you that turning on the electric current is the cause and the magnet moving is the effect.
All right, part 5, practice exam questions. Let's test what you've retained.
Okay, the foundation is solid. Let's jump into a rapid-fire pop quiz based straight off the source text. Treat these like the real deal, okay? First question. Let's start with the most direct observation from the whole activity. What exactly happens to the compass needle when the current is turned on in the circuit? Think about our mnemonic for a second.
Got it? The answer is that the compass needle is deflected from its original resting position. We physically see the needle twitch and change direction. This provides undeniable proof that a brand new, invisible force is acting upon it the exact second the power starts flowing.
Next question. In Activity 12.1, how is the straight, thick copper wire positioned relative to the plane of the paper?
The answer. The wire XY is kept strictly perpendicular to the plane of the paper. Remember how we visualized it earlier? The paper is flat and horizontal, and that thick copper wire plunges straight down through it.
Question 3. What specific action is taken to actually pass the current through the circuit? Let's test your knowledge of the precise procedural steps here. And hint, don't just say turn on the battery. What are the actual technical words?
The phrase you're looking for is inserting the key into the plug. Passing the current is achieved by inserting the key into the plug. That is the exact wording from your source text. Inserting the key basically acts as a switch. It closes the circuit and allows the electric current to flow continuously from the power source right through that thick copper conductor.
Question 4. What is the ultimate scientific conclusion drawn from the needle's deflection? This is the big picture question. It's asking why this experiment matters in the first place. Like, why is it famous enough to literally be in your textbook?
The crucial point here is twofold. First, the text concludes that the electric current flowing through the copper wire successfully produced a magnetic effect. And second, which is honestly way more profound, it means we can confidently state that electricity and magnetism are forever linked to each other.
All right, last question. Let's see if you can anticipate where your physics curriculum is heading next. Based on the conclusion of this text, what is the reverse possibility that will be studied next?
The answer is the electric effect of moving magnets. The text notes that, well, if electricity creates magnetism, we naturally have to ask about the reverse possibility, right? Like, what happens if we take a moving magnet? Could that somehow create an electric effect? That perfectly sets up your upcoming lessons.
Let's think about this exact quote right from the source. Electricity and magnetism are linked to each other. I want to wrap up this explainer by really reiterating this because it is the absolute most important takeaway from Activity 12.1. This single sentence is the golden rule you need to carry with you right into that exam room.